Okay, so here we go, and looking at paper 1. I did have a go at this earlier. Unfortunately, my computer decided to crash while doing it, hence why I'm doing this by covering up rather than writing on here at the moment, because it's already written on. So, working through, starting at question 1. Define the term algorithm. Well, this one comes up all the time. About what do we mean by an algorithm? So remember, there are 2 marks here. So thinking about that, there are 2 things we need to say. So first part, we need to say that an algorithm is a set of steps or instructions. So just like in a recipe where you're told the steps you need to do to make a cake. So that's the first part. You need a set of steps or instructions, a set of commands, anything like that. That's 1 mark. And then for the second mark, we need to make it clear that an algorithm's purpose is to solve a specific problem, to reach a goal. It has to be going somewhere. So there's your 2 marks. Moving on, question 2. Right, we've got 5 computer terms here. Abstraction, data type, decomposition, efficiency and input, and we've got to define what those mean. So we're told here about the possibilities of what they could be. So let's have a look. Breaking a problem down into a number of sub-problems. So you're breaking something down. If you put stuff on your compost heap at home in the garden, then that will break down and it will decompose. Breaking something down is decomposing. So that will be decomposition, C. The process of removing unnecessary detail from a problem. So when we're trying to solve something, we put away all the stuff that's nothing to do with what we're trying to do, and we only focus on the specifics. That is A, abstraction. Those are 2 terms that we must absolutely know straight off. Now the third one is slightly strange. Defines the range of values a variable may take. Now at first sight we're thinking, what's that? Well, obviously abstraction, decomposition we've dealt with, so we've got 3 left. Input, no, it's not input, is it? We're not telling it what to put into the computer system. Efficiency, nothing to do with that. B, data type. What's a data type? A data type is what kind of data you can put into a variable. Well, if you think about it, yep, that's what it's saying here. Defines the range of values, what kind of values a variable may take. So the answer to that is B, data type. Okay, turning over, and we're into coding, which is what the majority of this paper will be about. So let's have a look at what we're doing. So an algorithm's been developed to automate the quantity of a dog biscuits to put in a dog bowl at certain times of day. Okay, so what's going on here? Well, first of all, we're asking for some user input to say what time of day it is, and depending on what the time of day is it breakfast, lunch or dinner? And depending on which one it is, if the time is breakfast, we set the variable q to be 1, we assign the value 1 to q. Else if the time is lunch, then we assign 4 to q. Else if time is dinner, then we assign 2 to a. Else, so we've got an else at the end, that basically clears up everything that you haven't covered before. So in other words, if it's none of those things, we say we haven't recognized that time, we don't know what you're talking about. Then we come to some definite iteration using a for loop. A for loop, remember, climbs a variable starting at the beginning up by 1 each time until it reaches the end. So we're starting at 1 and going up to whatever q is. So if we put in lunch, q would be 4, we'd go 1, 2, 3, 4. So the first time through it's 1, then 2, then 3, then 4. If n, the number that's climbing each time, is less than 3, so that'll be the first 2 times when n is 1, then n is 2, then we'll dispense a chewy. If it's not less than 3, so it's 3, 4, 5, 6, whatever, then we dispense a crunchy. And we just go round and round and round until we reach the end value, which is q. Okay, let's have a look at the questions. Shade 1 lozenge, which shows the line number where selection is first used. So selection, when we're making a decision. Selection is always shown by if. So there's if, and it's on line 2. So line number 2 is your answer for that one. Okay, we need to keep that because we're going to need to keep referring back to the code. Shade 1 lozenge, which shows the line number where iteration is first used in the algorithm. So iteration, where we're repeating something over and over. But if is just going straight through. There's no repeating going on there. But a for loop repeats over and over. And that's first is shown in line 11. So your answer there is line 11. Moving on. Now, you've got to start thinking about these dispense biscuit calls. Shade 1 lozenge, which shows how many times the subroutine dispense biscuit would be called if the user input is breakfast. So let's go back and look at this. So, if time equals breakfast, so if when they typed it in, when we assigned the value to time, it was breakfast. If time equals breakfast, Q is assigned the value 1. So we can ignore all this stuff because we've dealt with the if. So Q is 1. For N is 1 to Q. Q is 1. So we're going from 1 to 1. And that's not very far, is it? So we start off that N is 1. Is N less than 3? Yes. We're going to dispense a biscuit. So we've done it once. Background we go. Have we reached the limit? Yes, we have. Q is 1. So we've reached the limit. We've dispensed biscuits once. That's all we're going to do. So if we go back to here, how many times will we call the subroutine dispense biscuit? Well, the answer is once. One subroutine call. Moving on. Shade 1 lozenge, which shows the data type of the variable time in the algorithm. The variable time. So what is time? Let's have a look. Time would be very tempting to tick off date time straight away, wouldn't it? But if we look back now at the variable, when we user input it, if time equals, and we've got something inside speech marks, a word inside speech marks. What do we call bits of text inside speech marks? That's a string. A string is a piece of text. Date time is a date or a time, integer is a whole number, real is a number with a decimal part. Let's move on. Right, now it's not about choosing a specific lozenge, it's about answering some questions. State how many times the subroutine dispense biscuit will be called with the parameter chewies if the user inputs lunch. Right, let's go back. How many times are we going to give out chewies? So if we enter lunch here, so lunch is put in, if time equals breakfast, it doesn't. Okay, else if time equals lunch, it does. Then Q is assigned the value 4. So now we know that Q is 4, else we don't need to worry about that because we've done it, and we don't need to do else because we've already got something. So Q is 4 when we get to here. So for N is assigned 1 to 4, Q is 4. So we're going to go through this loop 4 times. We've got to see how many times Chewy is going to be given out. So the first time round, N is 1. Is N less than 3? Yes. Okay, we're going to dispense biscuit Chewy. Okay, we're going to send Chewies into that subroutine. Fine. So once. We've done it once. Okay, onwards. No, we haven't done that. Right, back we go round. Now N is 2. Is N less than 3? Yes, it is. So we're going to dispense biscuit Chewies again. So that's twice we've done it now. Back we go around again. N is now 3. Is N less than 3? Nope. So we're not going to do that. So we're going to do this instead. We're going to dispense a crunchy. It's not a chewy. We've done 2 chewies. Now we've done a crunchy. Back we go again. N is now 4. Is N less than 3? No, it's not. So we don't dispense a chewy. We dispense a crunchy. So that's 2 chewies, 2 crunchies. Back we go around now. N is 5. Right, we've reached the limit. We were meant to go up to 4, so we're finished. 2 chewies, 2 crunchies. So, how many times are we going to be called with the parameter chewies? Twice. How many possible values the result of the comparison time equals dinner could have? Time equals dinner. How many possible values is the result of that comparison? Well, let's see. Time equals dinner. Well, if you think about it, time equals dinner is a Boolean statement. It can only be true or false. It either is dinner or it's not. So it can only produce the results true if time is dinner, or false if time is not dinner. That's two different things. So we're going to put down two possible values. And if you wanted to, you could write true or false. The programmer realizes they've made a mistake. State the line number of the algorithm showing in figure 1 where the error has been made. Now I hope that you immediately, when you saw this, you were shouting at the screen because you were saying, no, look, it says 1 is assigned to Q, 4 is assigned to Q, and then 2 is assigned to what? A? Well, obviously it shouldn't be A, should it? It should be Q. So we're in line number 7. So the line number 7. And what are we going to do? Write one line of code. So how are we going to change that? What should it say? Well, obviously it should say Q, shouldn't it? Not A. So all we've got to do now is say that the line should say Q is assigned the value 2. So instead of saying A is assigned 2, it should say Q is assigned 2. Brilliant. Okay, I think we're done with that question now. Let's move along. And on to, yep, done that. Okay, on to question 3. Right, bit of binary arithmetic. Excellent. So the following bit pattern represents a binary number. What is the result of applying a left binary shift of 2 to this bit pattern? Express your answer as a bit pattern. So a left binary shift of 2. So we want to move the number 2 spaces to the left. So this one here will move 1, 2. This one here will move 1, 2. So if you think about it, we're going to end up with a number where we've shifted the 1s 2 spaces to the left. We can fill in at the beginning. We've got 1, 2, 3, 4, 5. So we need 1, 2, 3 zeros at the beginning. And there's your left binary shift of 2 places. The arithmetic effect of applying a left binary shift of 1 to a binary number is to multiply that number by 2. So if you think about it, if you take the number 1, 0, which is worth 2, if we do a binary shift to the left of 1, we get 1, 0, 0, which is 4. We've doubled the 2 to make it 4. State the arithmetic effect of applying a left binary shift of 3 to a binary number. So let's think about it. When we move 1 place to the left, we double. If we move 3 places to the left, we double, then double, then double again. We double 3 times. So doubling gets us twice, doubling 4 times, doubling 4 times, 8 times. So the arithmetic effect of moving a binary number 3 places to the left is the same as multiplying by 8. To get the mark, you have to be talking about both things here. What will be the arithmetic effect of left binary shifting a number by 4, then right binary shifting the result by 5? So logically, moving to the left, whoops, there we are, moving to the left multiplies by 2, moving to the right divides by 2. Now, if we move 4 places to the left and then move 5 places to the right, if you think about it, we move 1, 2, 3, 4 that way, then 1, 2, 3, 4, 5 that way. It's effectively moving 1 place to the right. So think about it, we've gone 4 spaces that way, then we're moving 5 spaces that way, we end up 1 space to the right. If we go 1 to the right, remember going to the left multiplies by 2, Going to the right divides by 2, so moving one place to the right is the same as dividing by 2, or halving. You can say it either way. Okay, number 3 dealt with. Number 4. Here we go. Sound. We always love these sound calculations, don't we? Sound engineer is recording a singer. Describe why the sound must be converted to a digital form before it can be stored on a computer system. 2 marks. So clearly you're looking for 2 things about the process. So why does sound have to be converted to digital? Well, it must mean it's in some other form before we start. So your first mark, to get your first mark, you can say that sound is analog. Or you can say continuous, if you like. So sound is analog continuous data. And computers can only store digital data. The sound that's out there is analog, but computers can only store digital, so we have to convert from one to the other. There are your 2 marks. The sound engineer is using a sampling rate of 2000 Hertz. They've made it nice and easy for you. Everything is in normal units, Hertz, bits, seconds. So 2000 Hertz, sample resolution of 4 bits, minimum file size of a 5-second recording. So remember, our file size is sampling rate times sampling resolution times time. So the answer must be 2000 Hertz times 4 bits times 5 seconds. Write that down, you're going to get a mark. Work that out. Well, 2 times 4 is 8, 8 times 5 is 40. And then put your zeros on the end. So we've got 3 zeros to put on the end. And that is the number of bits. Now we've got to give the answer in bytes. How many bits are there in a byte? There are 8 bits in a byte. So that means we're going to need to divide that by 8 to show how many bytes we've got. 40 divided by 8 is 5. So that's 5,000 bytes. Thankfully for you, they've only asked you to give the answer in bytes. If they'd asked you in kilobytes, we'd have had to say there's 1,000 bytes in a kilobyte, it'd be 5 kilobytes. But that gets you your 4 marks. Okay, still carrying on with our sound. The sound engineer currently uses a sample resolution of 4 bits, which enables a sample to be stored as one of 16 different bit patterns. And again, if in doubt, put your little table down, whether it's for colours or for patterns, whatever. 1 bit gives you 2 bits gives you 4 patterns. 3 bits gives you 8 patterns. 4 bits gets you 16 patterns, which is what it says here. She wants to increase the number of bit patterns available from 16 to 32. Shade 1 lozenge, which shows the minimum sample resolution she can choose that will allow her to do this. So how many bits to get 32 patterns? Well, let's keep going. 5 bits, double, 32. Exactly what we wanted. So part B, 5 bits. Easy peasy. Shade 1 lozenge to show which of the following correctly states the effects of increasing the sampling rate. So if you have more samples per second, what is going to happen to your recording? So recording more detail every second. What will it do? Will it decrease the quality? No, of course not. Will it have no effect on the quality? No. Will it improve the quality of the recording? Yes. The more samples you have, the more it flows, and therefore the more it's like the analog signal. So it improves the quality of the recording, has no effect on file size. Well, no, that can't be right, because if you're taking more samples, you must be increasing the amount of data. Improves the quality of the recording, yes it does. Increases the file size, absolutely. Lozenge. Okay, number 4, done. Okay, we move on to doing a bit of coding ourselves. So now we've got to write an algorithm of our own. Now we're told that the subroutine Carter code, if we send it a character, it will tell us what the integer ASCII value of the character is. So if you send it the letter lowercase a, it gives you 97, because 97 is the ASCII value for lowercase a. Lowercase z, 122, and so on. Whatever you send it, it will send back the ASCII value. So we've got to develop an algorithm using pseudocode or a flowchart. Well, we're going to use pseudocode because it's a lot easier if we stick to pseudocode, to be honest. Asks the user to enter a character. Remember what I said to you before. Even if you don't know how to do the rest of it, do an assignment from user input. Gets you a mark. Output's lower if the user has entered a lowercase character. Output's not lower if the user has entered any other character. So basically, we've got to ask for a character and then decide, select if it's lower or not lower. So clearly, we're going to have to be asking for something, doing an if, and depending on what the result is of that if, outputting a value. So it looks to me like we've got a situation, we're going to input, then we're going to do an if and an else. So let's ask the user to enter a character. So I'm going to call it character. There's a good name for a variable if we want a character, isn't there? We're going to assign that from a user input. There you go, straight away. I think if I remember rightly from the mark scheme, there's 2 marks. One for using a user input and a second one for putting it into a suitable variable. Now we've got to make a decision about that. First of all, we've got to decide what the code of that is. So I'm going to get the code for that character. And to do that, I'm going to use, it says here, you must use the built-in Carter code character. So I'm going to use the Carter code subroutine to get the code for that character. There we go. So now I know what the code is. So we've assigned from that variable, we've sent off the character, we've used the subroutine, and it's sent back the code. So now we haven't got this, we've got these numbers. Now we're told here that a, lowercase a is 97, lowercase z is 122. So basically it must be a lowercase character if it's between those 2 numbers. So I need to use an if that checks if it's one of those. So I basically want to say that if my code is bigger than 96, so 97 and upwards, and my code is less than 123, that puts it in, so it's got to be bigger than 96, it's got to be less than 123, so that means it must be between 97 and 122. So if that's the fact, if that's a fact, then it must be lowercase, mustn't it? So I'm going to output. Now you must put exactly what it says. Must output lower. Okay. In any other situation, it's not lower. So the other situation, I use an else. If it works out like that, then I do that. Otherwise, else. Output, what does it say to output? Not lower. I'm going to put an end if. You don't have to remember that. If you do remember, that's fine. But if you don't worry. That's it. Done. Finished. I've asked for the character to be input. I've got the code for it. I've checked that it's in the right range. If it's in the right range, I've said lower. Otherwise, I've said not lower. That's everything it told me to do. 7 marks. Bang. Didn't even have to use that page. Very good. Okay, so what I'm going to do now is I'm going to stop there, and then we're going to move on to part 2 in a moment, where we'll do the second half of the paper.